thank you very much for coming. I am going to be talking about side effects, which I think every programmer I've ever talked to thinks that's not a big deal. And then I talk their ears off for 40 minutes to tell them why it actually is the biggest deal going. So thank you for joining me for that ride. You can no longer escape. My name is Chris Jenkins. Among other things, I am a podcast host. I host the Developer Voices podcast. We talk about the future of programming. We talk about the future of technology. And this is my chance to not be the host and talk about my perspective on where we're going as programmers and why Kafka really matters as part of that journey and why side effects are at the very heart, even though we don't even think about them. But don't subscribe to the podcast yet, because you're about to hear my voice for 40 minutes. You can make your decision at the end whether you ever want to hear me again or not. I'm going to start this talk properly with one of my favorite XKCD cartoons. If you really hate someone, teach them to recognize bad kerning. I saw this and I thought it was a funny joke, and then I went out from the office that lunchtime and I saw bad kerning everywhere, and it ruined my life just for like a few weeks, just seeing awful typography everywhere. It really is true that if you teach someone something small that makes the world worse, you can really screw with their minds for a few weeks. But the flip side of that is it's also the point at which I started to appreciate good typography and the effort that goes into making a good font and good layout and good graphic design. And I'm not a graphic designer by any means, but that's where my appreciation for good graphic design began. So I want to do something a bit like that. I want to show you a very, very small thing which I hope will make you see the ugliness in all the code we're writing and the ugliness in all the systems we're designing for the next few weeks. Hope it tortures you, because it will lead you to a better path for programming, I promise. So let's talk about side effects. I think they are an iceberg of complexity, and I'm going to explain why. Let me put it this way. I think every function that you write when you're coding has two sets of inputs and two sets of outputs. And you say to me, that's not right, Chris. I've been programming for X years. You have one set of inputs, that's your argument list. And then you have one singleton set of outputs, and that's your return type, right? But no, you have two sets of inputs and two sets of outputs, and it's really important. So have a look at this. Here's some familiar code. We're adding X and Y. Take two integers, return an integer, right? That's the familiar pair in action. But have a look at this code. Here, slightly out of date example, I want to know what's on TV at the moment. This is pre-streaming era. So I give you a channel ID, and it will go through the list of things that are on for that channel and find the one that's currently showing and return, optionally, a current program. The station might be off air at that time of night, who knows. Can anyone see the hidden input in this? Chris. Other Chris. Fetching the current time, right? So this code, the behavior of this code absolutely depends on what local datetime.now returns. It is absolutely an input to this function. The behavior of the function absolutely depends on it. If it changes, the behavior will change. And yet we don't tell anyone that it's part of the function signature. It's just magic hiding under the surface. Have a look at this example. I'm going to delete emails by search term. So I give you a regular expression, because that's how everyone wants to delete their emails. And you get a Boolean back saying whether or not you deleted some. This has hidden inputs and hidden outputs. The hidden input is the state of the inbox manager when you want to delete something. And it's not in the function list. It's not in the argument list. It's just hiding there. There's also the hidden output of the state of the inbox manager after you've called this function. And they are both absolutely inputs and outputs. The state of that inbox manager changes completely how this code will behave, and calling this code will change the state of the inbox manager. So there is a hidden set of inputs and outputs, as well as the ones we explicitly declare. And that's my definition of side effects. It's the hidden inputs and outputs that a function secretly depends on. If you start to see that, you can see it in code everywhere. I have a standing challenge. I often get into arguments about functional programming. I have a standing challenge with anyone who writes in something like JavaScript and says, I write in a functional style. Give me 150 lines of your JavaScript code and I will find you side effects. You do not write in as functional style as you think, because it's hard. But side effects, hidden inputs and outputs. So what? You're at a Kafka conference, who cares? Is it a big deal? It's a very big deal, and I'm going to tie this all the way through to the large scale of systems architecture. But let's start small. What's the effect of side effects on testing? It's fairly horrible. We write some code like this: delete by search term, regular expression, Boolean on the output. How do you test that? You can't test it because you can't supply the inputs. You can't check the outputs. So we all do exactly the same thing. We create a mock object, and we smush it inside the code, and then you call this function, and you check the mock object afterwards. But you're not really testing it. Well, you're not really testing it properly because you've just admitted you cannot test this code without breaking it open and seeing how it behaves under the hood, and then writing some magic code around the side to exercise the code that you can't see but you know is there, right? Much better API would be this. You give it the state of the inbox as you're calling the function, and you expect the state of the outbox as a return type. If you did that, you wouldn't need mock objects to be set before and checked afterwards, because the function signature is honest about what's going on. It tells you what it needs, tells you what it supplies. Some people dislike the second function signature because it's more complex. I don't think it is. I think it's exactly as complex as this code is, and no less complex. Right? It's not an oversimplification. So if we start to make our inputs and outputs explicit, we can get to a point where we can actually test code as a black box without having to look under the hood and see how it's implemented and depend on how it's implemented. We can just depend on its behavior. Connected to that is the problem that if this is just happening in testing, we have the same problem when you go to things like publishing APIs and publishing contracts, because they're never the whole story. There is always the explicit set of inputs and outputs and the hidden set of inputs and outputs hiding under the surface that we assume are there in exactly the same way as this inbox manager. Now, if you're Java programmers, you already know this is a problem, because I bet as Java programmers, you've downloaded the third-party library, and you found the method that you want to call, and you call it, and it explodes with a runtime exception because you didn't call the right setters to set it up. So you could dive into the source code and see what it actually needs, but you don't. You just look at the setters, and you call a couple of them, and you run it again, and it blows up again, and then you call some more setters, and you run it again, and finally it works, and you convince yourself that you finally configured this object correctly. And you have to do that dance so often in Java because the function signatures are lying to you. They're only telling you part of the story. They are trying to hide complexity in a way that we would call, I don't know, encapsulation, but really they're just sweeping it under the rug. This gets really bad when you're trying to compose larger systems that you're writing in code. So you will have heard, I think, probably, favor composition over inheritance. That's a common mantra in Java. The way we write Java, and Java the language, honestly, it does not enable you to do that very well, because it's supposed to work like this. You call a function, and it's got a certain output type that goes into the input type of the next function, and that outputs something, and you just chain them together, and you make a nice chain of code. That's what it looks like in theory and in the textbooks. In practice, most of your code actually looks like this. You've got the input and the hidden inputs to function one, and then that spits out the output you use, and something has happened in the hidden outputs. And then the function you call next is depending on some inputs, and gradually this set of hidden inputs and outputs aggregates to be larger than the whole of the thing you're trying to compose. And what happens, typically, traditionally, is we sweep that complexity under and under the rug until one day someone says they're trying to debug something, and they say, I don't know why it's behaving this way. and I can't figure it out, and it's not behaving rationally. The system's got too big. Those guys wrote the code beforehand are bozos. We should rewrite this entire system from scratch in my favorite programming language, and then it would work sensibly. Because we all think that it's the bozos in the last project that screwed it up. But no, structurally, the complexity is constantly hiding itself underneath until you drown in it. And what actually happens if you go through with that rewrite is the whole team loads this hidden dependency graph into their short-term memory. You rewrite the system. Now everybody on the team knows how that hidden behavior works implicitly. And when the staff turn over again in the space of about 5 years, all that folk knowledge is lost, and the call to rewrite from scratch happens again. All because we're sweeping complexity under the rug until it drowns us. Hidden dependency graphs are a huge source of complexity, and they all come out of side effects. But it actually gets much worse than that. This idea of hidden complexity, I think, is absolutely awful. When I first learned about this next bit, literally, it kept me awake overnight, because I suddenly had this feeling like the whole of programming was just this messed up illusion of safety. You ever had that feeling? Maybe you have. So my hope is that this will keep one of you, perhaps the nerdiest person in the room alongside me, keep you up tonight. So, data. We have hidden complexity in data itself. Let me ask you a quiz question. Have a look at this code. I'm going to make it a tiny bit bigger if I can for the people at the back. No, I'm not. That's going to take too long. Okay, people at the back squint really hard. Can anyone tell me what this code will print? What it does is it takes a list of things, adds cat to position 2 in the list of things, and then prints out the thing at position 2. It's not, well, it is a trick question. Of course it's a trick question, but the trick is not that it's an index out of bounds exception. Anyone know what this will print? It prints, element number 2 is dogs. Why? Because threads. Threads. Now, why do threads make a difference, and why are they side effects? Because your piece of data, your array that you thought was yours to manipulate, has a side effect. It has a hidden input of the behavior of anyone else who happens to be manipulating that list. Every piece of data in Java potentially has the hidden input of the behavior of whoever else has access to that reference. Data itself does not sit still. We cannot even rely on data in our systems. You think you've got a 5, maybe you have. Maybe someone else thinks they've got a 5 too. I think it's nightmarish that our problems in programming go right down to the level of data. And on the day I retire, I'm going to give this talk, I'm going to get it to this point and just say, programming is awful. Peace. But I sort of have to stick around and give you some hope. So let me give you some sources of hope on how we can kind of untangle this ball of hidden inputs and outputs. There is a traditional approach to this that we're used to. If even data itself can be manipulated under our feet, the traditional, very Java-y approach to solving this is we take our data and we put a wall around it. And we say, because this data could move under my feet, nobody's allowed to access this data. I will federate access. You can talk to me if you want to see the data, but you can't use the data. It's imperfect because we tend to hand a reference back to an object that we think they're just supposed to read, but we have no guarantees. But we have this approach of, okay, I've got my data, put a wall around it, put up a barrier to the way people access it. Because otherwise I can't stay on top of how my data's behaving. If you zoom out and do this on a larger scale, we're also doing exactly with one style of microservices. There's one pattern of microservices which behave exactly this way. Put a wall around it, put a local database around it, hide access, and the game of building large systems will be, if you need to change my state, you talk to me. If you need to read my state, you talk to me, and we'll go back and forth, building our little walled gardens of data. That might sound familiar to Kafka people at this point. We're getting there. That's one approach, and you know what? It's got us to 2023, and isn't the world glorious? Almost flawless. So, I mean, that's one way to solve the problem. But there are other solutions. There are other approaches to dealing with this problem of side effects in data. One that I'm going to briefly mention, which I like to just get the ball rolling, is Rust. So the interesting thing about Rust is it's specifically designed, I would say, from this lens of looking at the world through side effects. It's designed to say, well, what if we just dealt with one side effect, which is the side effect of someone having access to a piece of memory? If we just leverage some computerized, automated technology to ensure that only one person owns a piece of code at one time, and so we're not opening ourselves up to the hidden input of other people's behavior. And it works really well for that kind of memory management stuff. And anytime now I would want to use C, I use Rust instead, because it solved that problem, which comes up all the time, memory management in C, right? Tracking the ownership makes concurrency easier, as well as lots of other things, right? It's almost an after effect benefit. Once you've tracked ownership of data and you've ensured that there isn't a hidden input to it, a lot of programming gets easier. And almost by kind of knock-on effect, concurrency becomes easier. So Rust is really great for threaded programming, almost by accident, I would say. I'm sure the Rust designers think it's by design. I think it's almost like a happy consequence of keeping track of side effects. That's one approach to stopping data moving under our feet, but we have others. There is another. We can go even more hardcore on stopping people manipulating the data under us. We could say, you can't. You can't change data. If I write some data, I can't change it. You can't change it. There are no hidden inputs to data because it's just data. It's supposed to stay put. And you have the idea of immutable data structures. Changes the way you program slightly, but instead of me giving you a list of things and you changing it, you give me a list of things as a reference copy, and I create a new list of things which has cats in it, and give that off to you. And at no point is there a single data structure that can be manipulated under your feet, because we've eliminated the possibility of a hidden input to the data. It is just data. Some people don't like that idea. They think, surely that's slow if we're copying all these lists around and copying maps and everything. They are, I'm afraid, wrong. We figured this out back in the 90s. We can do this efficiently. It's been productionized in just about every programming language. And if you take one practical tip away from this talk, please start using immutable data structures, because they will change the way you program in a good way. And it will ripple out almost to the point where I think you could reconstruct everything else I'm now about to say, because it will change the way you think about data, which changes the way you think about programming itself. Actually, I don't need to try and persuade you. I can appeal to authority on this. I can quote from the Oracle docs. This is officially a good idea. Maximum reliance on immutable objects is widely accepted as a sound strategy for creating simple, reliable code. I agree with Oracle. I'm not 100% convinced that the person that wrote that knows why. And I hope now we all know why immutable data structures matter. It's because they make data side effect free. Data just becomes data. And that raises a question, because if we put a wall around our data purely to stop it moving under our feet, we could start to open up our data again. If we have immutable data structures, we're no longer protecting our data just to try and stay sane. We can give people free access to our data because no matter what they do, it can't change where we think we are in the world. We can give them access to the data without them becoming a hidden input on the complexity of our system. We might choose to protect data for security reasons, but we're not building a structure that guards data just because things would go to hell if we didn't. Okay, that's data. What about other side effects? This is the moment some people who know me have been waiting for, the moment when I get into a Kafka talk and mention Haskell, which has a really interesting approach to side effects in general. I'm not going to totally try and sell you on the idea of Haskell. I'm going to try and sell you on a larger idea, if I may. But before that, we have to talk about quick syntax primer for Haskell, just enough that we can talk about it. So let's take our function to add cats. Takes a list of things and a position, and we'll add cat to that position and returns a new list, because it's an immutable data structure. That's a Java API. If I first take away the word public and take away the names of the variables, so I've just got the type signature. That's a thing that Haskell does, which I like, but that's another talk. And then we, so the next step, and if you're a JavaScript, TypeScript programmer, this will be familiar, we put the return type at the end, which I always thought was way more logical, because we read left to right, and having the return type at the end of the process seems logical to me. And then we just do a bit of smudging around with the syntax, and we get to this. So in Haskell, add cats would be something that takes a list of strings and an int, and eventually returns a list of strings. That's how you can read that. Okay? So let's have a look at that delete by search term function. Right? It's going to take a regular expression and the current state of the inbox, and it will return the pair of a Boolean and the new state of the inbox, which will be an immutable copy based on the original, right? So I looked at that code, and almost immediately, just seeing the type system, I saw a refactoring for that. You shouldn't be returning the inbox state and a Boolean about whether it changed. Just optionally return a new inbox state. That's modern Java programming, right? Optional. I like optional. Now, that's enough Haskell syntax to talk about the trick that they pull. If you squint at that code and look at the word optional and think of it as not an option of inbox state, returning the inbox state in the context of this may or may not happen. So we'll just say this is, we're returning an inbox state in some context. And the particular context is, maybe I will, maybe I won't. Optional. This is the trick that Haskell pulls to put side effects into the type system where we can track them. So let's have a look at some code that does that. This is a register user function. And the way you write it in Haskell is it would look like this. You take a username and a password, and you return a user in the context of having access to a database. Right? That's all that's saying. So you can have different contexts for different side effect types, and you can make your own if you want to. And it goes into the function signature. So there's still, in a way, there's still a side effect, but it's not hidden. It's an explicit change to the world. And now that it's in the type system, we can get the compiler, the programming language itself, to assist us in tracking that complexity. So I've got some code here, right? Calculate tax payment. Takes a list of transactions and returns an amount that you have to pay in tax. And then record tax payment. It takes your user ID, the amount you want to pay, and will return you a receipt from, what do you call them over here? IRS. IRS receipt, provided it has, in the context of having access to the web through HTTP and access to logging, because you probably want to record this locally, right? Okay, so now I go and I write a function that says handle tax. That takes a user ID and a list of transactions and will give you a receipt back, right? That's what I want to write. The compiler now has enough information that it can say, that's wrong, you are lying, this will not work. It's not possible to take a user ID and a list of transactions and get a receipt ID back because you've ignored the side effect, the context, the hidden thing of you need access to HTTP and access to logging. So the compiler can track that side effect of needing to access the database and propagate it through as you compose functions up. Now, this is great because just imagine you wake up one morning and someone says, do you know what? There's a massive security vulnerability in a popular logging framework. That could happen. It's possible. It could happen, hypothetically. So I look through my code and I try and figure out what the impact of logging no longer being reliable is. And I can say, well, look, handle tax is definitely affected because that has the context of logging. Record tax payment is definitely affected because that has the context of logging. But calculate tax payment, I don't need to review that code. I don't need to worry about that code. It never used logging, and I've got a guarantee from my computer, from the system compiling things, that there's no way logging affects that code. So when there's a security warning, because I'm tracking my side effects and I have a computer assisting me watching the complexity of the system, I can see the impact site of changes both external and dangerous, and colleagues that are writing other bits of code, if that's a different thing. So we can bring the computer to bear on this problem. It can help us. And that's what I really want to get to. I'm not trying to sell you on Haskell. I'm trying to sell you on the idea that we can move complexity tracking into the type system. And I hope one day, Java's doing a great job of stealing ideas from the functional programming world and importing them. And it's really making the language more usable. And I really hope somehow someone figures a way to do complexity tracking in the compiler in this kind of way. I would be far happier if I just got one wish that Java support us doing this than everyone become Haskell programmers. It's a close-run race, but overall, I'll take the other win. OK, enough about programming languages, because we are mostly at a systems conference, I guess. So what about larger systems? What else can we do? Well, with our lens of keeping track of side effects and not having hidden inputs and outputs, imagine that we have some code that wants to talk to another system, and it says, I'm going to deposit money. And in a traditional approach to this, you would write some code that says, deposit money, I'm going to call you with a reference to the accounting service, a reference to my user Alice, and $5,000, euros, pounds are all the same currency these days, roughly. I look at that code, and hopefully some of you look at that code with new eyes and say, my favorite argument in that is the 5,000, because it's just data. It's just a value. It sits there and stays put, and nobody can change it. 5,000 is a nice immutable thing. Not so happy with Alice, because it feels like she could be moving around just as I'm calling this function, and she could have changed by the time I get it back. So how about we change that to a reference, a unique ID for Alice? That's, again, immutable side effect-free data. I like that. I now feel happy about 2 out of 3 arguments. And I start looking at the accounting service, the reference to the accounting service. That's bugging me. Can we do anything about that, though? We need to access the accounting service. That's kind of inevitably a stateful thing that we need to talk to. I think we can do this. I think the way we've been experimenting with testing in recent years says we can go another step. And instead of referencing the accounting service directly, we can use exactly the same trick we used with Alice. We can have an address that points to where the accounting service is. And our code now has 3 immutable static pieces of data as its inputs, and no hidden inputs. And we will rely on some other mechanism, which we'll talk about in a minute, to cope with looking up that reference to the accounting service. And we'd actually end up with something like this. We'd end up with just a packet of data that says, what are we doing? We're depositing money. Where are we depositing it? Depositing it to the accounting service using these 2 bits of data as arguments, right? If we went from using mutable objects to just writing down data and sending it, we have accidentally invented actors. That's the actor model. Don't process it, just tell me where to ship the message, and I'll deal with it. And this is actually quite a nice approach, right? We can evolve on it, but it's quite a decent approach. We send messages across, and someone else is going to process immutable data on the way in, do something with it, and maybe emit more immutable data on the way out. And it's kind of a universal machine, this approach, right? Data comes in, we do something with it, data goes out. You could model it like this, type signature. A machine is just something that takes a state of the world and a new fact and returns the new state of the world and maybe a list of facts that it's caused to come out, right? And if you've ever played around with, let me think, Elm, maybe Gren, Redux, React and Redux. This is a really nice way of doing front ends, because you've just got data coming in from the back, and it changes the state which you then render out, right? It's a universal machine for doing data processing, in which all the inputs are just static data, and all the outputs are just static data. So, I've just thrown in the Haskell equivalent of that type signature for the people that are really tempted now to have more Haskell in their lives. This is pretty good. There's one big side effect in a system like this, which is glaring to me, which is if that processor goes down, all the messages get lost, which seems weird to me these days. That all those facts coming in, we're sending it off, but if there's a network problem, everything falls on the floor. And so almost inevitably, someone who likes the actor model but has unreliable systems ends up inventing queues. Because you've got immutable data, it's easy to write it down. You might as well write it down, and then someone else will pick it off the queue when they're ready, right? But that still bugs me. I don't like hidden stateful things where I can avoid them. And the problem here is that every time we read one of these facts to process it, it falls off the edge of the world. There's a hidden output to processing a new fact, which is that you destroy it. Reading immutable data is somehow a destructive operation. And so by pulling on this thread of side effects, we eventually say, hey, let's write it down and not delete it, and we have suddenly reinvented Kafka. Immutable data comes in. We can rely on immutable data because no one else's behavior is affecting it. We write it down because it's so easy to write it down, we might as well start, and we can process it through a universal state machine which can model just about anything. We've known that since Turing, I guess. Alan. Nice one, Alan. You predicted Kafka. And that's it. That system is about as side effect free as we can manage. And it's about as hidden complexity free as we can manage. That's why I like Kafka and functional programming at the same time, and I see them as exactly the same thing. And then we get this side effect benefit. Wrong choice of words. Then we get this additional benefit, which a lot of business people will talk about, and it is definitely like a business sell benefits, not features thing. But again, it's almost an accidental thing that comes out of this model. Having written down immutable data and deciding not to destroy it when we use it, we can start to reread it in different ways. And suddenly we've got an architecture where we no longer need to put a wall around our data and hide it from people just to make it sane. Because it's inherently sane, we can open it up to the world. And that starts the ball rolling on things like data as a product and less federated access. And you want this data? Sure. There's nothing you can do that will damage me by you reading it. Again, with the caveat, we might lock it out for security, but we're not locking it out just so our systems remain sane and predictable. We can open up the world of data with a universal, about as side effect-free system as we can manage. So, one more time, let's talk about side effects. Back in 2006, there was a paper called Out of the Tar Pit, which is something of a classic in certain subcultures in programming. If you've ever done any closure, you've probably heard about it. It's quite a good. There are flaws in it. It's rather over-optimistic about how good business people will one day be about being very, very specific about what they want. But the one point it makes, which is really good, which is that there are two kinds of complexity in our systems we're building. There's inherent complexity and accidental complexity. Inherent complexity is the IRS say these are the tax rules. As a systems builder, there's nothing you can do that will reduce the complexity of the tax code. It is what it is, and you have to deal with it. And then there's inherent complexity, and there's accidental complexity. The accidental complexity is all the complexity we build for ourselves while trying to build solutions. And I think if you pull on this thread mentally and you start to see the world through the lens of side effects, so much of that complexity is hidden inputs and hidden outputs sinking beneath the surface of our systems. So, I will say it one more time, and I hope I leave you with it, because if you think about it for long enough, you'll reconstruct the whole of this talk. Side effects are hidden inputs and hidden outputs that hide beneath the surface of your code, and they should keep you awake at night. Thank you.